Okay, so sorry for the inconvenience. Can you go to the next slide? So I am Christophe Simon-Boisson, working in Thales.
So something is now it's working.
Okay. Okay. Yeah. So so Thales is a large company, by the way, but in lasers, Thales is specialized in solid-state pulse lasers, and in particular short pulse lasers. So Thales is not 30 years like shown in the slide, but now 40 years, by the way. And Thales has specialized for a long time. Few years after CPA apparition, has introduced CPA products in the early 90s, and in particular high peak power lasers. So we did introduce a petawatt laser. We reached petawatt 12 years ago with a system at Berkeley in the US. And more recently, 5 years ago, we achieved the 10 petawatt peak power with the INP system in Romania, which is still a world record. I don't have time for this, but another kind of extreme lasers is the lasers we have on a Mars planet, and it's very tiny lasers, very robust, because one of them is working now since 12 years on Mars ground and still working well. So to perform a spectroscopy analysis using LIPS spectroscopy. Can you go next slide, please? Okay, so on that picture, I show some summary about the what we call HPLS 10 petawatt laser at INP in Romania, which is the most powerful laser in the world. So this laser was completed in 5 years ago in 19, and with an extension of beam transport, which was commissioned the year after. So the particularity of this laser is that it has there are two beam lines, two identical beam lines, which are seeded by a single front end based on OPCPA, and it is based on several TISAF amplifiers. You see on the bottom left corner the synoptics of the system. And we developed the amplifier as well as the pump laser. So you see on the bottom right corner the picture of the laser. And for those you want, there is a link to have a sort of guided tour of the laser if you go to use that link. Next slide. Yes. So that's summary of the commissioning we did with the beam transport in 2020. Was done by the way, at the time of the COVID, and we managed to do some on-site commissioning tests with the laser, but was also a large broadcasting over the world with Gérard Mourou and 250 scientists attending online, and we demonstrated these more than 10 petawatts. So I'm not going to give many details, but you see below the three series of 10 shots. So it was really a one shot per minute. If you see the time tag on the x-axis, you will see there are all the shots which have been fired successively, and you see different graphs with the pulse duration. So the pulse duration in that case was in the range of less than 22 frames per second. So please, next slide. So the message I want to give here is this laser is now online. From the beam lines, the transport lines were equipped also with focusing parabolas, which were for the 10 petawatt beams that were installed in 2022 and 23. And the commissioning of the 10 petawatt beam was starting in 23. So there were the graph you see here is that kind of experiments, commissioning experiments with the lasers firing on solid targets, and you see that on the graph the proton cutoff energy which were reached for different target thickness. So, and in that case, the laser was used close to the maximum intensity it can deliver, which is basically 6 to the 22 watt per square centimeter, and it's in that case it was a little bit less because the team was using a plasma mirror in order to further improve the contrast. Also, it's already naturally very good, but for proton experiments is the most demanding one, so you need to provide the best possible contrast ratio for the pulses. Can you go to the next slide, please? Yeah, so that's another experiment. It's right now I think some people or all of you know that there is a bit of enthusiasm for laser fusion since in particular since the results from NIF in 22 and years after. And there were also some startup companies which were appearing in the field of laser fusion. And one of the examples of this company is Marvel Fusion, which is a German company. And the people of Marvel Fusion, they have with Eli NP and us some collaboration agreement, which led also to further improve the laser, but also to provide beam time on Eli NP. And what you see on the slide is experiments done with the 1 petawatt beam. And this year in 24, they have done first experiments. They have made 2 campaigns, one in the spring and one in the summer, with the 10 petawatt beams this time, with the further improved contrast. Of course, it's very recent, so the results are not yet fully exploited. They are still undergoing some analysis, but apparently they are quite promising, and it means that these, of course, there are also beams at Eli, at the other Eli, which can be used also for laser fusion, and there is a big, quite energetic nanosecond beam in Eli Prague, which also very well. Very much demanded for fusion experiments. So that means one is it's important to say that there is some practical experiments for the science which now these facilities which are online. And I think it was mentioned by Roland that today is the last day for the Eli Eric users call for access, and within this call, I think there's the first time where the 10 petawatt beam from Eli NP is proposed for user access. So it's very important that now so some years ago we developed these lasers, but now they are online and already providing results for the research community. Can you go next slide? So the second part of my talk is application for laser plasma acceleration. So I think we have some common pictures with our amplitude colleagues, and I think that's the right picture. You have you saw it already in the presentation of Pierre-Marie. So just I don't insist. I think you can go to the next slide because Pierre-Marie was explaining the big advantage of the laser. So what I want to do is to just insist a bit more on this slide. Again, I think Pierre-Marie disclosed one important thing is that to go for practical experiments and practical applications, we need more flux. So we need to increase the repetition rate of the lasers. So that's something we want to do. And in our case, we decided the strategic decision was to keep the titanium sapphire technology because it's naturally providing very short pulses, less than 30 femtosecond, but even less, let's say, even less than 25 femtosecond is in quite a routine way. And we decided to launch a development of a 1 joule 100 Hz laser, so based on titanium sapphire, for a large bunch of applications in science, industry, and medicine. You see 2 examples. Below you see the logo of Horizon 2020 project, which is called Multiscan 3D. So the project now is well engaged. It will finish next year. So about developing some configuration of laser acceleration, in particular large charge acceleration schemes, in order to go further and to provide some solution for people needing to develop these systems of cargo screening. And there are some companies in the world developing such systems for harbors or for borders, and they need some practical solutions. And in that case, they want to move towards the 3D imaging. This is a feature they don't have yet. So laser is not really completely arrived. I think there is still some let's say research and technology development to do, but I think we are now closer. And another application you see on the right is sorry, maybe the picture is not that big, but the idea is also to explore electrons, high energy electrons, as an alternative to X-ray therapy, which is a standard today for radiotherapy, but also to protons. So the electrons have some advantages over protons. They can be easier to accelerate because accelerate protons to 200 MeV, which is the level required for cancer therapy, is a bit hard with lasers. So right now the community is improving, but is not completely there. And electrons are easier to accelerate, and also electrons, they are a bit broader spectrum. They don't have this Bragg peak feature as protons exhibit, but it means also that this very sharp peak, you need a lot of control to be sure that it stops where the tumor is. Electrons is a bit softer spectrum, energy spectrum, so it can be a bit easier and safer to manipulate. So we have right now, there is a EU project led by Professor Malka at the Weizmann Institute, and Thales is going to provide a laser for the research, and of course that's is not to the point where the medical usage is there, but we are also considering that it could occur someday in the future. Next slide, please. So in Thales, we had launched this development, and we have also a collaboration, a structural collaboration with a very famous French lab, LOA, Laboratoire d'Optique Appliquée. And we have decided to create a joint research lab on Plateau de Saclay, which is called Heracles, which involves also Lully, so for different topics related to high intensity laser and their application. And within this project, so there is a construction of a new acceleration platform. So you see different drawings and different pictures. And so this acceleration platform will have, you see on the bottom right pictures that the laser is going down towards a radio protected area. And there is also room for extension later on with potentially a second radio protected area. And this platform we are supposed to develop so electron acceleration, but also X-ray, gamma ray production through different techniques, which can be Bremsstrahlung, which can be ICS, and different configurations. So it's a long-range project. We are right now, if you can go to the next slide, we have already, you see in the picture, we have a first laser there. The laser is right now, we have an amplifier running, and it will be online as a compressed beam as a 200 millijoule level. If you see the synoptics on the left. Oh, I have echo. Sorry. I try to go to the end. And an interesting point is that in that case, the pump laser of the TISAF amplifier is a diode pump laser, which means that they makes the overall laser system more efficient than flash pump based systems. Following this 200 millijoule beam demonstration in a few weeks from now, we are targeting to have the 1 joule version with adding a big amplifier, a large amplifier, 1 year after, which means we should have 1 joule available at the end of next year. And regarding the 200 millijoule beams, so we'll have one at this joint research lab at LOA, but also we are working with a company which is developing these acceleration solutions and also this secondary radiation solution, which is called TOR System, which is an American company. And this, I think the apparition of this company on the market is really the proof that there is a huge potential for these laser-based acceleration and radiation generation solutions. So just I think I have one more slide to present some results we achieved. So you see that the results of the amplifier. So before the compression, you see on the left the energy after amplifier, also the stability, which is quite good. So I heard that in Swissfeld presentation was energy of 0.8% RMS. Now we can produce 0.3% RMS, which is also comes from the very high stability from the pump from the diode pump pumping lasers. We did some contrast measurement. In that case was very good because if you see the contrast only 10 picoseconds before the main pulse is 10 to the 8, and it was specified 10 to the 6, and it was 10 to the 8, so it's almost 100 times better. And the pulse duration, in that case, we took the full aperture, but we're attenuating the energy because we didn't have the vacuum chamber for the compression at full energy, and we got a 23 femtosecond pulse. And I think that's it, and I thank you for the listening.